Hey there, YouTube follower. I'm gonna try another advent of code. I did film a YouTube video yesterday for day 16, but never completely solved the problem, so I probably will not upload that one. Okay, moving on to day 17. I'm excited to try this one out because even a novice like me might be able to solve it. Uh, Maybe I won't read the whole thing. The idea is of physics projectile motion. You have an x position, a y position, and x velocity, a y velocity. We'll update the rules in just a bit. Starting from 0, 0, the particle takes a somewhat parabolic path, and depending on what you put in for the initial velocity in the x position in the x direction, the initial velocity in the y direction, the path will be a bit different. And what you're given for your target puzzle input is visualized by this square here. It's called the target area. And the puzzle maker wants you to keep track of when your particle lands in the target area, but because we're thinking about this in discrete time, 1 second, 2 seconds, 3 seconds, etc., does your particle land in the target area on an integer valued time value? And if it does, for the sake of having something turn in at the end, what was the highest y position you got through all these trials? So what I think I'll do is I'm going to try this in R. Give me a minute to get things up and running here. And we are in day 17 already. Puzzle input, I could just copy and paste that one line here. What I think I want to do is call the left endpoint TA, the right endpoint, that is in the x direction, TB, the bottom of the rectangle, TC, and the top of the rectangle, TD. Now, for reasons that will become apparent as we go along, I'm going to eventually make for loops, and I want these to be the maximum values of those for loops. But for what I have in mind, these sort of numbers I'm going to probably be adjusting the most. Now, for the initial velocities in the x and y direction, basically what I want to do here in the bottom left, I want to try out initial velocities going from, say, 1 to 10, and initial velocities in the y direction also going from 1 to 10. Now, what I'm thinking of doing is creating a huge data frame that will keep track of all this all at once. So I'm trying to avoid too many for loops. Now, in the data frame, I want all combinations of these velocities in the x and y directions. Now, let me lower the amount of numbers a bit here just so I could show you what I'm thinking. in R and in other programming languages, but other programming languages have this feature, but in R, what I'm looking at is the expand grid function. So v sub x are the numbers 1, 2, 3, 4. V sub y are the numbers 1, 2, 3, 4. And what expand grid will do for me is give me all 16 of those combinations. So rather than having to use 2 for loops, I'm able to now create this grid here so that we can keep track of all the initial velocities all at once. So I want v naught x to be from 1 through v max, v naught y to also be the same, 1 through v max, that is. We're going to start to create a data frame from that expand grid. And now we have all these different numbers to try for our initial velocity. I don't like how the default variable names here at the top left say var1, var2, so I'm going to change that. So now the data frame has an initial velocity and in both the x and y directions, I should say, sorry. Now we also need to keep track of the coordinates, just the xy positions. So now we'll create a new column x that starts at x equals 0. And also do the same for y. So that way we have the x and y coordinates right there. Now, along the way, I also want something called y max. And hits target. So now I have a column to keep track of the maximum y coordinate. Hopefully I'll be able to implement that. And a column that will tell us if we eventually hit the target on this particular path. That's supposed to be target. Okay. Now, for me, it's just easier to think of the xy positions before thinking about the velocities. So I'm just going to rearrange the columns a bit. I did a tidyverse technique, so I need the tidyverse. So now my data frame looks like this: x, y, v sub x, v sub y, whether or not we hit the target, and then the maximum y value. All right. So this is what the matrix looks like, or the data frame looks like at the start. Every single particle, every single one of our 100 particles at the moment, I could go to something like 1,000 particles. Every single one of our 100 particles start at the coordinate 0, 0. They're each assigned a different initial velocity, represented in the x and y directions. We're going to then update the positions and velocities according to the puzzle setup, and then deal with the last two columns in just a bit. So I'm just going to run this for one time step for now, just to make sure things are working okay. But moreover, now let's look at the rules again. And on each step, the probe's x position is increased by its x velocity. So, because I'm doing this over the entire data frame, I'm going to add the entire vectors. The probe's y position is increased by its y velocity. Here's where a little bit of physics comes into play now. Due to drag, the probe's x velocity changes by 1 towards the value of 0. That is, it decreases by 1 if it is greater than 0. Increases by 1 if it's less than 0, or does not change if it's already 0. I think the way I do that is with an if-else statement. If velocity is greater than 0, you replace this value with minus 1. I have a hunch this is something I'm going to have to worry about in part 2. At the moment, I'm assuming positive velocities in the x directions, but that's probably what I'm going to have to really update later on in part 2. Okay. And then finally, due to gravity, the velocity in the y direction decreases by 1, which means that the y velocity could eventually be pulling downwards, as well. So let's see how this all played out. Here's what the data frame looks like at the very beginning. So now in the x column, we should be adding what was previously in the vx column. In the y column, we should be adding what was previously in the vy column. The vx column should all decrease by 1, and the y column should all decrease by 1 as well. And I believe that all worked out. So now, for some more of the puzzle stuff, are the particles in the target area. So now, what happens is over the course of time, different particles might happen to be in the target area but at different times. So I want to make this program a little flexible to be able to handle that, and just literally add the words true if the particle is over the target area at any time, any integer value time. So now we have a vector where we're saying that the x value is greater than or equal to the left endpoint, and the x value is less than or equal to the right endpoint. The y value is greater than or equal to the low height of the rectangle. And one more, the y value is less than or equal to the top side of the rectangle. So in target now should also create a vector. Let me show you that here in the bottom left. Creates a also 100 element vector of Boolean values, true or false. Now to update this, well, let me just say it this way. We have hits target, take the previous hits target's value, or in target now. So if there are any new true values here, that'll make this whole statement true, and we get to save it. Now I also want to update the y max values, and I'm essentially taking the maximum of this y coordinate column, the second column here, and the last column. Now in R, if you said to do that, if you said take the maximum of the second column and the last column, it would take all 200 of those numbers and I'd spit out just one maximum value. What I want to do is actually do this pairwise, second column, last column. And the function in R is called pmax, parallel max. So I'm going to run this all again. And notice that in the right-hand column, the y values are kept for the highest that they got so far. And I'm thinking everything works okay. So I'm going to run this out to Tmax, the maximum amount of time, which I set at 10 seconds up here. Now, after some time, the x value is not changing anymore because there's literally no more movement in the x direction. The y values keep decreasing. Now, unfortunately, I don't think I have any paths that hit the target. That's not good. Oh, I meant to do this for the example. In the example, they had these values for the target area. So it was 20, 30, negative 10, and negative 5. While we're here, why don't I just kick up Vmax and Tmax? Okay. I'm going to go ahead and run the code. Now, in the second to last column, I have situations where the particles did hit the target. So what I'm going to do is focus on the rows where this word true appears, and then only in this upper half of the data frame where the word true appears, then simply pick off the highest y max to finish part 1 of the puzzle. There we go. So this emulated the part 1 example, and now I'm hoping to run this over my puzzle input. I think I'll time it. Now, part of what's going to happen is I still don't know how big the velocity or time values can be. I'm going to keep them at 25 for now. And I'm going to type these in, or this answer into advent of code, and it's not going to get the right answer. So I'm going to try again. Now, for my puzzle input, the biggest numbers were along the magnitude of about 200. So I'm going to increase my velocity max and T max to some bigger numbers. Maybe that'll affect things. So I got 210 for the Y value there. What if I just kept going? Considering my code's only taking milliseconds to run. So keep going. Shouldn't need to go too much further out. That might have been too much. Now my code's taking a while. Whoa. Uh-oh. So there were situations where the velocity in the x direction can be pretty small, but the velocity in the y direction could be pretty large. That's something to really be concerned about. Why don't I lower this value a bit? Maybe I don't need so much in the time particles. So let's see here. Should make this code a little bit more adaptable if the number of guesses I'm putting in the x or y directions are different. Maybe we'll try out this number here. So what I did was, my guesses for the initial velocity in the x direction goes from 1 to 67. My guesses for the initial velocity in the y direction go from 1 to 500. And then for each particle, I'm simulating a path of 500 seconds in time length, in time. Ooh, answer is too low. So what if I go further in the y direction, but maybe restrict the time to just 100? No? trying to think if there is maybe just a little more I can consider here without having to make my data frame too big. In the top right corner, my data frame now has 1,000 particles to keep track of. And I'm running them, what did I say, for 500, a simulation of 500 seconds. Still getting the same answer of 31,125. I'm gonna try to keep the velocities in the x direction down, but increase other things. So for vertical velocity is 1,000, but keeps decreasing by 1. It would take 1,000 seconds just to reach the top. What if I restricted the x velocity a lot? Maybe the vertical velocity increase a lot, but take time to 10,000? And there we have it. So that was the issue, is that if the particle has a lot of vertical velocity, the amount of time it takes to reach the top also takes a long time, at least according to this version of the physics. Right, that took me a little longer than I hoped to solve it, but let's at least look at part 2 while we're here. Uh-oh. Part 2. Maybe a fancy trick shot isn't the best idea. After all, you only have one probe. You better not miss. To get a better idea of what your options are for launching the probe, you need to find every initial velocity that causes the probe to eventually land within the target area after any step. In the above example, there are 112 different initial velocity values that meet this criteria. Well, if I look at my screen here at the top right, my data frame now has 692 rows. I'm just going to try that number. Dang, too low. So close. I don't know if I was close. Now, in the x direction, I think I only tried 10 values in the x direction. So I'm going to increase the amount of velocities in the x direction by a factor of 10. I don't know if that linearly increases the runtime. I'm going to run this now. And also I meant to copy and paste the second half of the instructions over here. At the moment, the data frame has 865 rows. I don't think this is going to be the right answer. I'll tell you why in just a second, but just in case it is, I'll just try it out. Nope, still too low. Okay, now apparently negative y velocities are possible, or definitely going to be a part of everything. So I'm going to continue playing with the values. Maybe bring this in. Also, I should try to replicate the example. So let's go back to the example. Velocity max. Not that I would know that off the top of my head, but let's go with 100, 100. Now in the y direction, we can have negative y values as well. I could change the description now. The number of distinct initial values that cause the probe to be within the target area is it's going to be the number of rows in the data frame. So again, I'm just trying to replicate the example at the moment, so hopefully this won't take too long. Uh-oh. Why'd I get 0? I'm supposed to get 112. I only tried about one velocity value. That's not good. And I got to 112 that the example stated. Okay. Now I'm going to bring in the puzzle, the real puzzle. The issue is I'm going to have to increase, most likely increase the velocity in time. And I don't know how much further out I need to go. In the top right corner, my data frame has over 2 million particles that we're tracking at the moment. there we go. Have it, folks. I think I got kind of lucky. I thought I was going to need to expand my code and search a little bit more. Got a code that had about a 2 minute runtime. It's not great, but at least it'll be easy for folks like us to understand. Alright, so I'll post a link to the code so that you could see it all at once. But once again, thank you for joining me on this journey, and I'll see you tomorrow for day 18.